Alrighty, y'all. Are you ready to learn? Today we're taking a look at the recitation for April 22nd. In this one, we're going to talk about rotational dynamics, kinematics, and obviously more with some torque stuff, right? So we start with a flywheel. Oh, I'm so good at drawing a perfect circle, right? And we have friction slowing it down. We're starting at an given initial velocity with a given mass and a given radius, and we're using friction brakes to slow it down. Okay? And we have each brake pad, 2 brake pads, and each one exerts a force of Fn. So, and we're given a coefficient of friction. So, right, we have 2/3 away from our center. There's our 2Fk. Right? 2 brake pads, one on either side, each exerting a force from friction. There it is. Right? And our initial, we can say our initial omega is this way. Because then this would be slowing us down. Cool. Wonderful. Great. Now let's figure out how we actually solve this problem, right? How long does it take to bring the flywheel to a stop? So the way we would approach this, right, if it was just linear, if we were saying how long would it take for friction to slow something down, we would do, right, our sum of our forces equals ma, and then we would use this acceleration to then say that, right, our v2 equals v1 plus at. Right? Our second velocity, right, we use this here. We know our second velocity is going to be 0 because we're coming to a stop. We have a given initial velocity, and all we have to do is use the a from here to solve for t. Well, it's the exact same thing in rotational motion, right? But instead of our sum of our forces, we get to do our sum of our torques equals, ooh, that's a gross looking towel, equals I alpha, right? Our rotational moment of inertia and our angular acceleration. And then the same way we use the kinematics equation here, we can use the exact same kinematics equation, but just in the rotational mode, right? Omega 2 equals omega 1 plus alpha t. Okay? And we know that our omega 2 is 0 because we're coming to rest. And we were given that this is just some variable omega. So all you have to do is get our sum of our torques, our I, so we can solve for alpha in terms of things we may know. Then plug it on in here and solve for t. And that's our problem. That is our final solution. So let's start figuring out some of our torques, right? So we have this force acting here. If I choose the center to be my pivot, then I can say that my torque, since it's going to be perpendicular to this radius, okay, our torque as done from that is, so some of the torques, there's just that one force acting, well, 2 of them, but it's going to equal 2 times, and our force due to kinetic friction is normal force times a mu k, both of which are given as just hypothetical numbers. I'm going to just put that here. Fn times mu k. And now we just multiply by the radius, right? And it's not going to be the radius of our circle. It's going to be our radius, our distance to our pivot, which we were told was 2/3 of that. So that's going to be 2/3 of r. And we know that since if I follow this arrow around, it will be causing a clockwise rotation of our thing, right? Because we're going counterclockwise initially, and it's slowing us down, causing an alpha to be clockwise. It's going to be a negative torque. Okay? So here's our sum of our torques equals I alpha. Well, we weren't told that I is a given variable in here, so let's break that up into parts as well. So for a flywheel type thing, we're going to use just our regular, for this one, we use that Ri, I don't know why I started up there, but we get that Ri equals 1/2 mr squared, same way we would for just like a solid disc shape, which is what a flywheel is, okay? Large spinning disc. So we get I is mr squared, m and r both being variables that we were told. So now if I plug all of this in and simplify this side a little bit, we're going to get 4/3r Fn mu k equals 1/2 mr squared. Okay? And then simplifying this a little bit more, right, I'm going to multiply both sides by 2, divide both sides by r, because again, oops, sorry, forgot to write the alpha there. I times alpha. All right, multiply by 2, divide both sides by r squared, divide by m, right, because we're solving for this alpha so that we can, our goal is to plug it in here to solve for t. So simplifying all this, we're going to get 8/3 fn mu k over m just comes here. The r squared and the r is going to cancel out to just leave us with an r there. Equals alpha. Wonderful, great. We got our alpha in terms of things that we know. Now we get to do the fun part and plonk it on into this equation here. Okay? So we already said that our final omega is 0 equals our omega. Right? And since this is a negative torque here, this is a negative alpha here. So it's going to be plus our negative alpha, which is 8/3 fn mu k over mr times t. Right? Oh, I didn't write the negative. I said negative, but I didn't mean it. Right? Negative torque gives us a negative alpha, and our omega's here. And we said that our starting omega was positive, but it doesn't really matter right now. So now we bonk this to this side. This is going to become negative, and then when I divide, the negative's going to disappear, give us a positive time. So simplifying all of this, I get to say that omega equals 8/3 fn mu k over mr times t. Solving for t, just dividing all this to the other side, we get that t equals 3 omega mr over 8 mu k fn. Right. Our time that it takes to slow down our flywheel in terms of variables that we were given. Wonderful. Okay. Next question, right? Now we're looking at some linked objects. We have a bucket hanging from a string that's wound around a pulley. Again, we're told it's a solid cylinder. Right? We're given the shape, and given that shape, we can get an eye. So keep that in mind for later. Right? So first thing we're going to do is draw a force diagram for our bucket and our pulley. So we have our pulley. Pulley is the thing that's rotating, so we get to draw an extended force diagram. So we have, right, if the string is wound around it, we're going to have our tension from that string pulling like that. And then my bucket, this one isn't rotating, we don't have to draw extended force diagram, just a regular one, back to our basics, right? We have gravity pulling our bucket down, and we have tension of that string pulling the bucket up, right? Because what's going on, we have our pulley, the string's wound around it, and it comes down, and here's our bucket, right? And it's unraveling down this way, so that's the force of that tension. Now, in terms of the force diagram, we just expression for our net torque, right? So here's our pulley. I'm going to pick my pivot here, right? Because that's what it's spinning around, and also technically, if I were to include, there's the mass of the pulley, and also something might have to be holding the pulley up. But whatever's holding the pulley up is acting at that center. So because I set that pivot, we can kind of just ignore that. We can ignore it anyways for right now, but really it's just helping us select that pivot. And now we can say that, right, in terms of the forces, we can say that our torque on that pulley is going to equal the tension in the rope, tension in the string, times the radius of the pulley. And since it's going clockwise, down this way, it's going around like that, that is a negative torque. Now we do Newton's second law for rotation, right? Sum of our forces equal ma, but instead sum of our taus equals I alpha. And then we do it for each object, right? So one moves, one turns. So I'm going to start with what moves just to keep our, start with what we're familiar with, right? So our bucket we have our sum of our forces, which is tension acting positive, mg acting negative. That's just how I'm choosing to set my axes. Right? Tension minus mg equals ma, a of the bucket. Right? Again, since we have multiple things going on, we have to keep track of our bucket versus our pulley. Oh, yeah, bucket with mass little m and a cylinder with mass big M. Right? That's going to be our distinction. Okay. So now I'm just going to come down to our sum of our torques for that pulley. So that's going to be, right, negative T times R, which is what we set up here. There's our torque on the pulley, and that has to equal I alpha. And right, our I for a solid cylinder, right, we're given that it's a solid cylinder up here. I is going to equal 1/2 big M R squared. Okay. Again, I'm just going to plug this in to make my life easier for right now. Negative TR equals 1/2 M R squared times alpha. Okay. So we have our Newton's laws of motion. Okay. And now we just have to figure out our relationship between the angular acceleration of the pulley and the linear acceleration of the bucket. Okay. So we know that however fast this bucket is accelerating, the string has to be accelerating with it. Right? So at this point on the bucket, on this point on the pulley, this point on the string is going to have the same linear acceleration as the bucket. So that's what we can use to relate this linear acceleration to our angular acceleration. So what we can say, right, the same way we do relationships with omega to get to linear velocity, we can say that our acceleration, well, really it's the acceleration around, right, the linear acceleration of any point around the circle. That acceleration equals r alpha. Okay? And since that string is holding it together linearly, making them related, you can say that this is going to be our AB equals r alpha. And again, this is our radius of our pulley. Cool. And there's our relationship. And it says it may be different depending on how we draw our pictures and choose our coordinate systems. Right? If our acceleration of the bucket is positive, the way I've said it was positive, so I said positive was up. So if our acceleration of the bucket was up, that means that our acceleration of our pulley at this point would be up. If I follow that around, that would be making us go counterclockwise, giving us a positive angular acceleration. So a positive linear acceleration gives us a positive angular acceleration, or a negative linear acceleration would give us a negative angular acceleration, meaning that this relation holds true and we don't have to think about any positive or negative signs. Now we just calculate our acceleration of the bucket. Okay, so I already set up some of my equations up here. I'm just going to steal them real quick. Let's steal this one, and this one, and I don't have to rewrite that one. That's fine. Right? So clearly our relating factors, right? We have a relationship between A and alpha, but we also have this same tension in both. So I'm going to solve this for my tension real quick. I'm going to get that my tension equals my MAB plus MG. Now I can take that and plug in over here. And I'm also going to plug in, I'm going to solve this for alpha. AB over R equals alpha. I can take this, plug in over here. Then I have everything in terms of AB and things that I know. And then I can just solve for this AB. So my TR, we said was MAB plus MG. Again, these are all little m's because this is our bucket. And that's going to equal our 1/2 big M R squared times, we said alpha was AB over R. Now we just do some fun algebra, fun and fresh algebra. We love algebra. to get some of this to cancel out. Right? R squared over R, that's just going to become, all right, 1R, just 1R in the numerator. Then there's an R on this side and an R on this side, so I get to cancel out those as well if I just divide from both sides. Right? And I'm just going to distribute in this negative to open up the parentheses and make my life a little easier. So now if I rewrite everything, I'm going to get that negative MAB minus MG equals 1/2 MAB. Cool. Now what I do, isolate this, get all the terms with AB onto one side. G equals 1/2 MAB plus MAB. Factor out that AB. Right. Divide, and then we get that our acceleration of the bucket is going to be equal to negative mg divided by 1/2 m plus m. Right? And just to make it a little prettier, I always like to multiply out this 2 and just multiply it on the top and bottom. Negative 2 mg over m plus 2m. Right? Equal to the same thing. This one just looks prettier to me. Doesn't really matter. You can leave it either way. But now we have to suppose that our pulley was a hollow cylinder with the same mass and the same radius, I assume. Right? Now we have to figure out what the acceleration would be now. Right? So the only thing that changes with the hollow cylinder is our I value. Right? So what we can do is really what we say is I equals lambda times mr squared. And this lambda is different for different shapes. Right? For a hollow cylinder, right, that lambda, I don't know, I have the eraser, I was trying to point. That lambda is 1 for a hollow cylinder. So now we just get to say that I equals mr squared. But really, if I carried it all the way through, we'd get to see that. So we just get to do the exact same thing. I pull these equations down, but anytime that I had the 1/2, we replace it with our lambda, right? Because that's the only difference. 1/2 lambda. I do the same algebra. I solve here, nothing changed for the bucket. Plug in over here, simplify things down. The r squared is still there. The only thing that's different is that coefficient. Okay? This is now lambda. Doing all my algebra through with this as lambda, all this algebra. Now the only thing that's different is instead of multiplying through everything by 2, lambda just being 1 means that if I just plug in 1 for that lambda, it already looks pretty. Right? So now I got the exact same equation that I had up here, but with lambda. But if I kept it as this solid cylinder, right, our solid cylinder, our lambda is 1/2. So if I plugged in 1/2 down here, that gives me my equation for our solid cylinder. If I plug in 1 for that lambda, that gives us the equation for the hollow cylinder. All right, well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this recitation or any other problems that you want me to try to explain, and I'll do my best to try to explain it because I guess Sydney explains stuff.